Okay, so
all right, so just make sure you look at those. If you have any questions, let me know. Those of you who
and
did
so basically,
pick the one,
it just kind of walks you through what each side should have. So,
wait, so do you want it to be like a rectangle, or do you want it to be like that? Oh.
I would prefer a tissue box. But I loved that he made his into a tissue box.
Oh,
that made my day. But so anyway, so you have your different sides, okay, and all the different sides are listed up there, okay. It's not a bad project, so get it over with. Seriously, do not wait till Sunday. Okay.
Did nobody donate tissues at the beginning of the year?
I didn't ask them for it because I do it. I just don't worry about it. Don't worry about that. Okay. Huh?
Are you gonna?
So, in front of you, you guys have this pretty little periodic table. I recommend at the end of the chapter, you guys take this and you put it into your journal. Basically what it has is it has your trends. So if you notice, you guys have little hearts and you have little atoms showing you sizes and electronegativity, okay? So we're going to review all that stuff today, okay? But this is always good. Let's add in a little thing to the top right here, though, okay, where it says Zeph. I didn't really teach you guys to use that word, okay, because it's really an abbreviation for effective nuclear charge. So don't worry about using that word. Just use the idea that it's the higher number of protons. What is increasing going across? What do we see on the periodic table increasing?
The protons.
We don't see the protons increasing, but we see the atomic number, okay?
But isn't it the same thing? Yeah.
They are, but I just wanted you guys to write that so that you can see that. Okay? All right, higher shielding effect. The other way that we've said it is more layers. All right? So as you move down, you're increasing layers, you increase that distance, that makes the interaction between your nucleus and those outside electrons act differently. Okay? Flip the page when you're ready. So this is what you have on the back. I just wanted to point it out just so you know that you have all this information here as well. Okay, and it kind of explains the ideas to you. Okay? All right? Then you have this page. From this page, really all that I need you guys to focus in on are these two guys, okay, Mendeleev and Moseley. So Mendeleev is the one that you guys had to watch that video on when I wasn't here. How did he arrange the periodic table? You have to be able to tell me how they both arranged it. So how did he arrange it?
Atomic mass.
There you go, atomic mass. Yep. Okay. And Moseley, how did Moseley fix it and arrange it? Atomic number, which is the number of protons. Okay, so he represented the number of protons with that atomic number. Okay. So that's really all you need from this page. I am planning on, sorry, I should have said this at the very beginning. I'm planning on testing you guys on Thursday. Because really, there's nothing left to teach in this unit. It's just practice. Okay? So, trust this.
Just that?
The whole packet. Yeah.
Damn, it's gonna be easy.
Trust me, it's pretty much done. You're good. You guys have been working on it. We're going to remind ourselves today. I promise you'll be fine. All right. Turn the page. So you have these two little half sheets. I am not going to go through these. This is actually straight from your POGL when you guys were studying Coulomb's law. Okay, but this has some of your vocab on it. It has atomic radius, and it describes that idea. It tells you your trends. It tells you about ions, ionization energy, and then the other side is just electronegativity. So really, only look at these pages if you just need a little bit more on what those words mean, okay? But if you understand it as we're kind of going through the little review today, you should be fine, okay? But these are just there just in case you need them. All right, this is the page that we are going to focus on today, okay? So this will be your nice little pretty sheet with all the information on it, okay? Okay. So, we've been practicing with trends, okay? So before break, we're going to try and remember everything that we were practicing, okay? So we do have trends on the periodic table. It's set up in a certain way, okay? And it's because all atoms want to have how many electrons in their outermost energy level? Anybody remember? All right, who does everybody want to try to be? Well, yeah, so 8. But who are they trying to be? They're trying to have the configuration of a noble gas.
Why does everyone be 8?
Just a second. Okay, so we just got the question, why does it have to be 8? So remember, your valence electrons include your S and your P shell, right? So your S shell only gets 2, your P gets 6, so 2 plus 6 is 8. So everyone wants to try to be one of these guys. They have a full shell, okay, a full outer layer, all right? And so just remember that when we start talking about the ions, okay? But that's why all these trends are also going to kind of exist, okay? All right, so atomic radius. Oh, wait. Before we do that, top corner. Does anybody remember we had this one thing? I just said it about 2 minutes ago.
Distance?
But it was about distance and it was about charge. And it was somebody's law that all of these trends are based off of. He's a cool guy. He's a cool guy. I was going for Coulomb's law because he's a cool guy. All right, that was your. It's all good. It's all good. We're gonna remember this. All right. So remember when you guys did a little activity on Coulomb's law? Okay, we were studying how distance and charge are going to affect how those that nucleus is interacting with the electrons on the outer shell. Okay. So remember I told you guys to think about magnets. So with distance, if I have magnets that are this close versus this close, okay, are these guys going to be as strong as these guys? No, they might not even interact with each other, okay? So as we increase distance, what happens to the force of attraction? It decreases, okay? All right. Charge. Charge is like saying a super strong magnet versus a super weak magnet, like the ones that don't even stick to your refrigerator, right? So if I increase how sticky that magnet is, it's going to have a bigger force of attraction, okay? So that's all that we're talking about. And when we're talking about charge here, we're going to be talking about how many protons this thing, that atom has, okay? So, so just remember everything comes back to those two ideas. All right. Atomic radius is just going to be the size of the atom. Okay. Something that you guys had kind of focused on was that we have a special corner over here and a corner up here. Okay, and that's kind of what all of these trends are focused, or not focused on, but based around. Okay, so they
Check out the F or like the empty space.
mostly the F, but it's just that corner.
The
We just
F?
usually talk about F, fluorine. So between fluorine and francium, which one was the bigger one? Who remembers?
Size? Oh.
Francium. Why francium? What does it have? Well, that's what I asked. But why does it have a larger atomic radius? What is, okay, so she just said it's down. So what does that mean we're adding? More layers. Good. All right. So we're going to put the word big on this corner. And we're going to put small over here. Okay. Yes, it is. All right. And the whole idea here is as we move down the periodic table, okay, we're adding more layers. Exactly. Okay. But what's happening if we were to say, why is fluorine so tiny compared to, say, lithium? What does fluorine have more of? Not distance, but what? Protons. I
Where's
think.
lithium at? It's the second one. Oh.
Okay, so we're increasing the number of protons, so that means we have more pull. So as you move from left to right, we're increasing the number of protons in the center of that atom, okay, or the nucleus, so they're going to be pulling more on the electrons. Now, is that true? Can we talk about their atomic number, say between, this is a side note here, between sulfur and tungsten? Should we be talking about their atomic number? Who has the bigger atomic number technically? Tungsten does, right? So does this argument work when we're dealing with things on different layers? No. Okay? The only way that the more protons, more pull argument actually works is if you are talking about being on the same layer. Okay? And we're going to talk, I'll give you guys more examples about that. Okay? All right. Ionic radius. So for ionic radius, did this trend really change much? As far as you remember? Because it's still size, right? So we still have lower and to the left tends to be bigger. Upper and to the right tends to be small. However, there was a break in this trend. Who remembers where that break kind of was?
Oh, it was
I heard somebody say it. The metalloids line, right? It's a stair step, but I'm not going to draw it because that'll be really complicated for me to do. So I just did a diagonal, and I'm okay with you doing that, okay? So it's the idea that there is a break in this trend between our anions, okay? Our anions, which are the negative guys, okay? The easy way to remember that is that anions has an N in it for negative. And then our cations. Cations have a little T in the middle that looks like a positive symbol. Those are positive ions. Okay? So, if you remember, actually, let's finish up with the trend and then we'll come back to that. Okay, so why does it increase in size moving down the periodic table?
More layers.
More layers. And why is it increasing going across?
More protons.
More protons. Okay, same arguments, same exact thing. Okay, let me write that. More protons. And then more layers. All right, cool. So now let's talk about these two words that I just threw at you, an anion and a cation. Okay, let's start with the cation over here. Okay, I'm going to focus in on, let's do calcium. Calcium's right there. Okay, so calcium, whoops, sorry. So calcium, okay, would normally look like that. Okay? Just a little atom, happy little atom. But remember, everything wants to have the same electron configuration as a what? As a noble gas. How far away is calcium from that?
A lot.
Remember, you can go backwards and forwards.
Oh, so 2.
Yep. So calcium can go backwards, right? 1 and then to 2, to argon. Okay? So what does it have to do in order to do that? Lose electrons or gain electrons? Lose electrons, exactly. All right, so we're just going to put a little note there. So it needs to lose, and how many electrons did we say? 2. Okay? If I lose 2 electrons, I'm going to have an overall negative or positive charge? Positive. Okay? So positive 2. You can put positive 2 or 2 plus. It doesn't matter. Okay? So now, this is the part that I told you guys was going to be more important to me. I don't care about the trend for this one. It's the same as your or your atomic radius, okay? What matters to me is what happens to your ions when they're positive versus negative. Do they get bigger or smaller? So if he just lost 2 electrons, did he get bigger or smaller, do you think? He got smaller, all right? So cations, because they're losing their little electrons, okay, these guys tend to get smaller. Whether it's +1, +3, +2, okay? And you can think of it 2 ways. The easy analogy way is the idea that if it loses something, it's going to get smaller, right? But does anybody know why it's actually shrinking? What's increasing on it again? The protons, exactly. So if I have more of a positive pull, I'm pulling in on all those electrons, right? So once again, it's kind of like that more proton idea, okay? All right, so let's focus in on anions, okay? Not onions. Okay, so anions, it's an A. It does look like onions. Now I'm never going to look at anions the same way. All right, so anions, okay, we're going to talk about, let's do sulfur. Okay, so sulfur originally looks like that. Okay, how far away is sulfur from having that noble gas notation? 2, right? 1, 2. Okay, so does it need to gain them or lose them? Gain them. Good. So we're going to say sulfur -2 because he's going to have an overall negative charge. Okay, so he got that from gaining 2 electrons. So what do you think his radius is going to now do? It's going to poof out, okay? So we're going to have sulfur 2+, and he's going to be humongous. So what do anions do?
Wait, why'd you put 2+?
Because I messed up. My apologies. I meant 2-. Good catch. All right, so anions tend to what? Get bigger, okay? When we're saying that, the only thing you are comparing that to is who it was before, all right? The neutral one. And this is going to be important to you guys when we start forming ionic bonds or crystal lattices, okay? So basically, between this sulfur and that calcium, okay, calcium needed to get rid of it, sulfur needed to gain it, so they're going to bond, all right? And in that process, calcium's going to get tiny and sulfur's going to get huge. Now, why did sulfur get huge? Besides gaining a couple electrons, what is the overall idea here that, what's making it poof out? It starts with an R. So you already had a cloud of electrons and then you shoved 2 more in there. What did they do?
Rearrange. Remove. Start with the R, right?
Yeah, it's repel. It's cool.
Oh, repel.
You were so close. Yeah. All right. So the electrons are repelling. Okay. And so if I do ask, sorry guys. So when you already have a cloud, the electrons don't want to be anywhere near each other. They have like charges. They're going to repel each other, okay? So this is the only new information. The rest of it's going to be a review. Are we all good on this? So the big idea here that I need to make sure you guys know is, do anions get smaller or bigger?
Bigger.
Bigger when they get charged, okay? And do cations get smaller or bigger?
Smaller.
There we go. All right. And the trend is the same exact thing as atomic radius with a break at the metalloids line. Okay, cool. Let's move on. Ionization energy. So ionization energy, just a reminder, is the energy required to remove an electron. Okay? So just like ions, right? I told you guys between calcium and sulfur, calcium is going to give it away. Sulfur wants to take them, okay? they require a certain amount of energy. So who between calcium and sulfur has a lower ionization energy, do you think? So remember, this is energy required to remove it. So basically, who's trying to give it away? Calcium is, right? So super low ionization energy. It doesn't require anything for you to take its electron because it's trying to give it away. Sulfur, does sulfur want to give any of his away? No, because he's 2 away. So he's holding on as tight as possible, okay? That's what ionization energy is talking about, okay? And if you notice, they both have the word ion in it, yeah? Ionic, yeah, okay. Just wanted to point that out. All right, so if I have low ionization energy, easier or harder to remove? Easier.
Oh,
You're good.
IE. Ionization.
And then if I have higher ionization energy, that means that it's what? More difficult. Totally writing all over my periodic. That's good. All right, so between, once again, francium and fluorine, who has the higher ionization energy? Who is holding on so tight because he does not want to lose any? Fluorine. Definitely fluorine. So we put a big heart on this corner, and you already know your noble gases are holding on. They have huge ionization energy. And francium gets a little itty bitty heart because he doesn't need.
Oh, that's why you have a heart.
That's exactly why, yep.
Wait, what do the hearts mean?
Fluorine is holding on for dear life. So holding on to his electrons because he loves his electrons because he only needs one more. And then francium could care less. He's like, please. He's like paying you to take his electrons. Do you have negative ionization? All right. Okay. So let's talk about the why, though, because you guys need to know the why. Why going across is fluorine holding on super tight? What does he have more of?
More protons.
More protons. Okay, more protons in the nucleus. That means you have more pull. Okay. Sorry, I'm going to have to write my arrow here. Sorry. If you want to put yours on the outside, you can. Why is francium not holding on to its tight? He has more layers. Okay, so we can say more layers, but why does that matter? What did we just increase if we added more layers? We increased the what? The distance, yeah, the distance, right? So think about those magnets again. If I have 2 magnets here versus 2 magnets here, are these 2 magnets talking to each other, the ones that are way out here? No, they're not going to be attracting each other, okay? So when we increase the layers or more layers, what we're talking about here is bigger radius or more distance, okay? All right. Finally, electronegativity. This one is important for our next chapter, like super important. You're going to be doing some calculations with it, okay? So it's important for bonding. Because basically, if you have something that's more electronegative than the other one, it's going to be pulling on all the electrons. And if it pulls on all the electrons, everybody like leans to one side, and then it's a lopsided molecule. And if you have a lopsided molecules attract to lopsided molecules. And then they like make solids versus liquids, okay? So we're going to get there later. But electronegativity is just an atom's ability to attract electrons. Okay. So, do you think we're talking about big, small, or do you think we're talking about hearts in terms of the trends? It's attracting electrons. Hearts. It's going to be the same as the heart, right? So little francium doesn't really attract them because he's trying to get rid of them, right? Fluorine, super attractive. Okay? I know. All right. So fluorine, everything leans towards fluorine. Fluorine messes things up sometimes. It's fun. All right. So let's finish up with why does fluorine Super electronegative. What does he have more of? More protons. So more protons, more pull. Okay, going down. What happens? More layers. Okay. When we have more layers, yep, we increase that distance. I just had more room. That's the only reason I'm writing this. If you want to, you can. More distance, less force. Coulomb's law. Okay? And that is it for the notes for this. Okay? So, are there any questions over these 4 big ideas here? No? All right. Flip the page or whatever. Go to the next page. Okay. Right now, silently, I would like you to do 1 and 5. They are not multiple choice. They are parts of a question. So please don't pick A, B, C, D. It happens every class. All right. So these are not multiple choice. They are parts of a question. Go ahead and answer them. In 3 minutes, we'll check back. Okay? Okay, you guys ready to look at answers? Okay, for number 1. Number 1 says, which of the following neutral atoms, so we're not talking about ions here, are going to be bigger, lithium or sodium? What'd you guys say? It's definitely sodium. Good. Why? More what? What? Shout it. Layers. More layers. Okay? You guys being pre-AP have to be able to tell me that. Okay? More layers. All right. By the way, just to be clear, when I say more layers, what we're talking about is that increase in energy levels. Remember for electron configuration, you had energy levels, which were the different periods? That's really what I mean by a layer, just to be clear. Okay. Nitrogen or oxygen?
Nitrogen.
It's nitrogen. Why? No, that won't work. Ideas? What does oxygen have more of? Protons. So what does nitrogen have less of? Protons. Has less protons. If I have less protons, I have less of a pull. Right? So less protons. That is an ugly less.
Oh, I was kind of confused.
Sorry, there you go. I'm going to get back used to this. All right, atomic number 12 or 18? Are these guys in the same row or column? Row, right? They're across. So, which side is the bigger side, left or right? Left, so 12. Good. Okay. So, why is 12 bigger? It has what? Less protons. Okay. All right, and then finally, atomic 12 or 56? 56, because what?
More layers.
More layers. All right, so do we see that the whole idea here is you got to decide, is it an up-down thing or is it a side-to-side thing? If it's a side-to-side thing, you got to check to see, are they in the same row? Okay, and if they are, then that's where your number of protons or your atomic number is going to play a role. All right, look at number 5. Easier to remove an electron from lithium or cesium? Definitely cesium. Okay, cesium has more what?
Protons. Layers.
Layers. How about fluorine or iodine? Iodine, because it has more layers. Okay, so one example that I pointed out earlier today, and I do want to show you real fast. Let me compare something like chromium and lead. We're going to do that. Okay? If I were to ask you between chromium and lead, which one has a higher ionization energy? What's your answer? So between chromium and lead, everybody look, because you're going to get asked this. Chromium and lead. What's your thoughts?
Lead.
Yeah, it's tough, right? What was my question? Higher ionization energy, right? Okay, sorry. Let me write this down so that we don't forget. I'm working off like 2 hours of sleep. All right, more ionization energy. All right, so ionization energy, we know the trend is that this is the corner that's huge, right? And this is the one that's tiny. So we want to be somewhere over here, right? So how do I decide that? Because we were kind of split half and half. Some of you guys said lead, some of you guys said chromium. Okay, so, and it's okay. This is why we're doing this. So just a second. Let me draw you guys a quick picture. All right, so chromium. What row is chromium on, you guys? 4? All right, so 1, 2, 3, 4. And he's got an electron there. I don't care about the number of electrons. All right? Okay. Am I wrong?
No, you're right.
Oh, but he's back on 3. We're just going to go with a general idea. Do we all understand that chromium is actually on 3rd energy level?
Yes.
Okay. All right. Don't forget that stuff. All right. Okay. Lead. Let's just go with the general idea here. What row does he go on? 6, right? So 1, 2, 3, 4, 5, 6. Okay. He's trying to talk to an electron way out here. Which one is holding on to their electron tighter? Definitely chromium, okay? So just know that those layers, that rule kind of outdoes the atomic number one. The only way that atomic number thing works is if you are on the same energy level. You have to be on the same energy level. Otherwise, lead technically has more protons, right? But it doesn't really matter because he's like super huge, okay? All right. Okay, just to be clear, this one is extra credit. Like I said, I'm trying to test you guys on Thursday. So that would be when this would be due. It's kind of a good partner thing. I still got 2. Don't you dare. Stop it. Okay. All right, this is what we're going to focus on tomorrow, but I will tell you all my other classes already graphed it. So what I would do is make sure you're ready to knock that out quickly so that you don't spend all class period tomorrow doing that, because you're going to eat up your practice time. So I already graphed it for you. You just have to connect the dots. If you're going to work ahead and do this at home, please, please, please make sure you follow Rule 4 and Rule 7. Okay? Because they tell you not to connect certain dots. So make sure you guys are ready for that tomorrow. Okay?
Follow Rule 4, don't.
Huh? Follow Rule number 4 and 7. Okay? Otherwise, we'll work on that tomorrow. Make sure you're getting that element project done. Okay?
That's due Monday, right?
Yep. All right.